Hello everyone. In this video I'm going to describe and demonstrate how to calculate the duration of a bond, the modified duration of a bond, and the convexity of a bond. And then we're going to take a look at some actual bonds and how duration impacts the interest rate sensitivity of the existing of the real bonds. Just to start off with a little bit, duration is a measure of the interest rate risk of the bond. It's an indicator of how much the bond's value will change with a change in its yield to maturity. And I've given you the equation for it here, and what this equation says is that we calculate the duration, also known as Macaulay duration, as 1 over the price multiplied by the time period t multiplied by the cash flow that is received by the investor at time t divided by 1 plus the yield to maturity raised to the power of t. We're going to also discuss how duration changes with a change in the coupon rate and the initial yield to maturity or the time to maturity. Modified duration has historically been used as a way to estimate the change in bond value due to a change in the bond's yield to maturity. And the way we calculate it is just to take the duration that we calculated, the Macaulay duration, divided by 1 plus the yield to maturity divided by the number of coupon payments per year. And then I give you the way to estimate the change in the price here. We're not going to actually estimate the change in the price because nowadays it's just as easy, if not easier, to calculate the actual change in price due to the change in yield to maturity. And I'm also going to demonstrate how to do this with some real bonds. Some people consider modified duration as a better measure of interest rate risk than Macaulay's duration, and so that's why I'm demonstrating how to use it here. I'm also going to demonstrate how to calculate the convexity of a bond. So if duration is the first order approximation of the change in a bond's value with respect to its change in the yield to maturity, convexity is the second order approximation of the change in a bond's value with respect to a change in the bond's yield to maturity. Convexity is really the curvature of the graph of the bond's price as it relates to changes in the yield to maturity. For bond investors, holding all else equal, they tend to like more convexity because, in what I've got stated here, the greater the convexity of the bond, the greater the increase in the bond's value with a decrease in the yield to maturity, and the less the decrease in the bond's value with an increase in the yield to maturity. In other words, as interest rates change, the greater the convexity, the better the outcome to the investor. I'm going to show you this how to calculate it for our sample bond, and then what it looks like for actual bonds. Okay, so let's go to the spreadsheet. So we've got a little sample bond here. In our example here, there's no basis convention. We're assuming 365 days a year that the bond earns interest 365 days a year. So we're not going to use any of our bond conventions here or our price or yield functions in Excel. We're going to do that on the next page. We're going to use the present value function here to calculate the value of the bond today. And then we're going to calculate by hand the duration and the modified duration and the convexity. And then we're going to use the Excel functions for duration and modified duration to also calculate those, just to demonstrate what that looks like. So let's go ahead and start up here in the value today. So here we're going to put equals negative, and our function is going to be present value. The rate is our yield to maturity. The number of periods is going to be 10 because we're looking at a 10-year bond here. Our payment is going to be equal to our coupon rate multiplied by our principal value. And our principal value, we're assuming here, is $1,000. Our future value is our principal value. And then our type is 0. We're going to get our coupon payments at the end of each period rather than getting our first one today. Let's put that in there. And we get a value of $926.40. I put a negative up here You can see that here. Because we would have gotten a negative value for this had we not, because it would have been a cash outflow, what we wanted to put in today. Now, I did name some of these cells, and you can see that in the spreadsheet that I put online. And I named cell B2 coupon 1. And I named cell B5 principal 1. Payment here, I put this in the count so it counts the number of payments. You can just put 10 there if you want, or you can just go ahead and fill this in as well. And let's go ahead and do that. So our payment's going to be equal to our coupon rate. And again, I named our coupon rate coupon 1 multiplied by our principal value, or principal 1. There we go. And so I'm going to pull this down all the way. Well, almost all the way. And so this last time period, though, we're going to receive our principal value plus our coupon payment. So it's going to be equal to coupon 1. Oops. There we go. Multiplied by principal 1 plus principal 1. Okay. And so that's all the cash flows of our bond here. We're going to get $50 at the end of each year, and then we're going to get $1,050 at the end of the time period for the bond on the maturity date. So now I'm going to calculate my duration. And so I'm going to put in here equals, and just to go back to show you what I'm doing here. I'm multiplying T by CT. I'm going to put in here equals T, which is our year, by the cash flow we're going to receive in that year. And I'll pull this down all the way. And then in our next column, we're going to find the value of 1 plus the yield to maturity raised to the value of T. So I'm going to put in here equals 1 plus. My yield to maturity is the value in cell B3. And I want to lock that in place. And I'm going to put in raised to the power of T. And what this says is it discounts that cash flow back to today. I'm going to pull that down. And that's actually what we're going to do in this last cell. So this is our discount factor. And now in this cell here, we're going to take equals our time times the cash flow, and we're going to divide it by our denominator there and get our values here. So now we're going to calculate the sum of the time period multiplied by the cash flow for that time period divided by 1 plus the yield to maturity. And then we're going to take the current price and taking that sum divided by the current price, or 1 multiplied by 1 plus that 1 divided by that price. Okay. Taking the sum and multiplying it by 1 divided by the current price gives us our equation here. So I'm taking this sum and I'm multiplying it by 1 divided by the price, or just taking the sum divided by the price would give you the same answer. We get a duration of 8.02, and this would normally be referred to in years, so 8.02 years. And then I'm going to use the duration function in Excel. And it's going to look a little bit messy here because it's not really made for this type of a sample bond. It's really made for an actual bond, and we're going to demonstrate that next. But our settlement is our settlement date, the date that a trade would settle on. And we're going to use the date function here because it requires a serial number for the date. So I'm going to put in date and then the year. We're just going to put in 2000. You can put in really any year you want here. The month 1, the day 1. And this is a 10-year bond, so I'm going to put in a comma here. So our maturity is our maturity date for the bond. It's a 10-year bond, so I'm going to put in date and then 10 years later, 2010. 1, comma 1. Again, it doesn't really matter the dates you put in here. They just need to be 10 years apart. The next is our coupon rate. The yield to maturity, 6%. The frequency, there's one payment per year. And then the basis in this case is going to be the actual. And so we're using a 365-day year or 366-day year for a leap year. And the actual number of days in the months. That's what this duration function would look like. And it gives us the same answer. So we're just kind of checking that answer there. So the modified duration, let's go out to that. Modified duration looks like this. We're going to take the duration that we just calculated up here, divided by 1 plus the yield to maturity, and that yield to maturity divided by the number of coupon payments per year. In this example, there's only one coupon payment per year, so we're just going to take 1 plus the yield to maturity to calculate that modified duration. So I'm just going to take the duration here of 8.02 divided by 1 plus the yield to maturity of 6% in B3 there. I get my answer, 7.57. Now we're going to use the M duration function in Excel to also calculate the modified duration. And again, we start here with the settlement date. Again, we're going to put in date. I'm just going to use the year 2000. Again, you can use any year. We're just going to we just need to have the right number of days, or excuse me, the right number of years apart for our example here. So I've got my settlement date in. My maturity date would be date, and then 10 years later in this example. And then a comma. The coupon rate is 5%. The yield to maturity is 6%. The frequency is 1. And then the basis is the actual, it's the 1. Okay. We get a modified duration again of 7.57. Okay, so now that's duration, that's modified duration. Again, those are measures of interest rate risk for the bond. Now we're going to look at convexity. And convexity is a little bit of more of a bear to calculate. Excel doesn't have a built-in function for convexity. We're going to calculate it by hand here rather than using a function. And going back to our document, so to calculate convexity, we need to find the sum of each of the cash flows multiplied by the value of time squared plus t divided by 1 plus the yield to maturity raised to the power of t. We're going to take the sum of those, and we're going to multiply that sum by 1 divided by the price today, and that price multiplied by 1 plus the yield to maturity squared. Okay. So we'll start here by calculating the value of t squared plus t. That's just the time period in years. So t and we're going to square that plus the time period. And now we're going to take CT So the value here, that's the payment, is CT, divided by 1 plus the yield to maturity raised to the value of time, and that's the value in this column D, multiplied by T squared plus T. So we're going to make this equal to our payment. Oh, okay. We're going to make this equal to, open parentheses, our payment divided by our value in column D, close parentheses, multiplied by the value in column G. And so our first value here is 94.34. I'm going to pull this down all the way. And then I've already put in here, so we're going to put in here sum highlight our values, and you should get a value here of 75,537.49. So going back to our equations here, we've calculated now the sum of this value. Now we're going to multiply that by 1 divided by the current price of the bond, and that price multiplied by 1 plus the yield to maturity squared to calculate our convexity. Okay, so I'm going to start with the first argument there, equals 1 divided by, open parentheses, the current price multiplied by 1 plus the yield to maturity, B3, close parentheses, up caret, squared, close parentheses, multiplied by our sum here, to get a value of 72.57. Okay. So when we're comparing bonds, again, holding all else equal, the greater the convexity, really the better the situation is for that bond investor should there be a change in the yield to maturity for the bond. So let's take a look at a couple things here. First of all, what is the duration of a zero coupon bond? Well, we can calculate that pretty easily here by just taking the coupon rate and putting in 0. So all of our coupons are equal to 0, and we get a duration of 10. So the duration of a zero coupon bond is equal to its time to maturity. Okay, that's important to note. Also, unless the bond has some feature that would increase the duration, the greatest the duration can be for just a regular vanilla bond is its time to maturity in years. Okay, so I'm going to put this back to 5 so you can see that again. Let's go out here to our notes, and I'm going to scroll back up to answer the questions I have here. So how does the duration of a bond change with a change in the coupon rate? So as the coupon rate increases, the duration of the bond goes down. The initial yield to maturity, holding all else equal, the lower the initial yield to maturity, the more sensitive the greater the change in the duration with a change in the yield to maturity. And then finally, the time to maturity. This isn't a perfect relationship, but in general, The longer the time to maturity, the greater the duration of the bond. So let's go back out here to our spreadsheet. We've completed this spreadsheet. I've demonstrated what happens with a change in the coupon rate. Certainly we can take another look here. I'm going to change the coupon rate now to 10%. We can see our duration went down. And again, the higher the coupon rate, the lower the duration. And that's because you're getting more value early on whenever you own a high coupon bond. And so it's going to be less sensitive to changes. The value of that bond is going to be less sensitive to changes in the interest rates. And you can see also that convexity decreased there too whenever we did that. So now let's go to sheet 2. On sheet 2, I've got 3 different bonds. They're all by Walmart. I wanted to use the same company and they all have the same bond rating. Walmart has a AA bond rating. I'm using the settlement date of 6/20/2024. I'm recording this on 6/18/2024, and I've got the actual ask price for the bond out there and the actual yield to maturity. We're going to verify these, and we're also going to use our calculations for the ask price to demonstrate the sensitivity of the value of the bond to a change in the yield to maturity. So I'm going to calculate the duration of each of these bonds, and then I'm going to demonstrate how that duration relates to the sensitivity of the price of the bond to the change in the yield to maturity for that bond. So again, we've got 3 bonds out here. The first bond matures on February 15th, 2030. The second bond matures September 1st, 2035. The last bond matures April 1st, 2040. None of these bonds are callable, and that's important here because that can affect, the payoffs and the convexity of the bonds. Again, I'm recording this on June 18th, 2024. If I bought this bond today, it would settle in 2 days. In other words, the cash, and the transaction would be finalized 2 days from now. So we're using a settlement date 2 days from now as a result. And then the current yield to maturity on the bond quotes are given here: 4.381% for this first bond, 4.763% for the second bond, and 4.955% for the third bond. And the coupon rates are up here as well: 7.55%, 5.25%, 5.625%. Bonds are quoted with an assumed principal value or par value of $100. So these are all premium bonds, and that's because the yield to maturity for each one of these is less than the coupon rate. So now I'm going to calculate the price of this bond using the price function in Excel. So I'm going to put in price. The settlement date is 6/20/24. Again, that's 2 days from when I'm making this video, so that's the day that the transaction would settle. Comma, maturity date is 2/15/2030 for our first bond. Our rate is our coupon rate, and that's 7.55%. Our yield is the 4.381 yield to maturity. Redemption, that's the value we would receive at maturity based on the quote method of the bond. So it's $100. Our frequency, these are all corporate bonds in the United States. They have a semi-annual frequency. In other words, you would get a coupon twice per year. So I'm going to put 2 there. And then finally, the basis. Again, these are corporate bonds traded in the United States. Most of those are traded on a 360-day count basis, assuming 30 days per month, 12 months per year, so 360 days per year, and the interest accrues based on that basis. So we're going to put 0 in there. And so I get the same answer. It's nice just to double check that, but also because we're going to use this calculation down below to demonstrate how that value would change if there was a change in the yield to maturity for these bonds today. Finally, I'm going to put in yield here just to again demonstrate how to do this in Excel. We're going to put in equals yield, So the settlement date is the same as what I mentioned before. The maturity date for our first bond is February 15th, 2030. Our rate is the coupon rate. The price, PR, stands for price. That's our ask price here. You can use either one. You can see they're the same. There might be a small rounding difference between the two because the source of the data only goes out to thousands, so there might be a small difference there. Our redemption is still $100. Our frequency is still 2. Our basis is still 0. And we get the same yield to maturity there, 4.381%. I'm going to pull that across. And you can see all of these, at least at the thousandths percent, match up. Okay. So the duration of these bonds, I'm going to put in equals duration. And again, our settlement date is the same. Our maturity date is the same. Our coupon rate is the same coupon rate. The yield is the yield to maturity. A frequency of 2. And then a basis of 0. I'm going to pull this across. So you can see here there's a wide range in the duration. And for our first bond here, it has the lowest duration because it has the lowest time to maturity. The yield to maturity is a little bit lower here, but that would actually cause the duration to be a little bit higher. However, the time to maturity is pretty short, relative to the other bonds here. And so because of the high coupon rate and shorter time to maturity, this one has the lowest duration and the lowest, as a result, interest rate risk of the bonds. As the time to maturity increases, we can see that the duration increases. Our last bond here has about 16 years, a little less than 16 years to maturity. Our middle bond here has about a little over 11 years to maturity. The coupon rates aren't horribly different between these two. You do have a pretty big difference in the coupon rate between the first one and the second and third bonds. So now we're going to put in a new calculation here, the new price, and the new price if the yield to maturity changes. So I'm going to put in here equals price. The settlement is going to be the same. The maturity is going to be the same as what we had before. The rate is the coupon rate. Here's where we're going to make a change. We're going to say the yield to maturity is equal to our yield to maturity here plus the value we're going to put here in C15. And I've named this cell CIYTM, so change in yield to maturity, CIYTM. The redemption is still 100. The basis, or excuse me, the frequency is still 2, and then the basis is 0. And so I get the same price here because I haven't put a value in this cell here. I'm going to pull this over. I can pull this over because I named my cell here. And so when I pull that over, that name continues on with that. So that cell is locked in place. And just to demonstrate, I can put in here, 0.02. So that means that the yield to maturity would be 2% higher. And we can see the new values, those bonds go down in price quite a bit, especially those last two, because they have high durations. Okay, because they're sensitive to a change in the interest rate. And as interest rates or the yield to maturity increases for a bond, the value of that bond is going to decrease. So let's go ahead and fill in. We're going to make a data table here, and then we're going to graph our answers. So I'm going to set bond 1, bond 2, and bond 3 equal to the values that we have in row 16 that incorporate that change in the yield to maturity. I'm going to pull that across here, and I can set this back to 0. It won't have an effect on our table here. So now what I'm going to do is highlight columns B, C, D, and E, pull that down for rows 19 through 40. Okay. And now I'm going to go to Data, go to What If Analysis, and Data Table. So we're not going to put anything in for the row input cell because we don't have a variable going across the rows, but we do have a variable here, and this is the change in the yield to maturity. So our column input cell will be cell C15, the one that I named and that you have named in your worksheet there, CIYTM. So this is going to show us the values of those bonds given a change in the yield to maturity. Okay. So your data table should look like this. So we can see here bond 1 has the lowest duration, and if the yield to maturity decreases by 4%, the value of the bond would increase to 140.05, and if it increases to 6%, the value of the bond would decrease to 88.10. That is the least amount of change that we have of our bonds, and that's to be expected because it has the lowest duration. We can see as the duration increases for the bond, the variability in the bond price given a change in the yield to maturity becomes greater. Okay. So I'm going to hide row 19 here. And I'm going to graph my bonds and the change in the yield to maturity just to show you what that looks like. So I highlighted everything here from rows 18 down to 40 and columns B through E, and I'm going to go to Insert and go to Charts, and I want a scatter or a bubble chart here. I'm going to use that one there. So you can see here that if I were wanting a bond with the least amount of risk, I'm going to go for bond 1. The change in the bond price, these are the bond prices or bond values. The change in the bond price has the lowest change in the bond price with a change in the yield to maturity. The bond with the greatest convexity, it's not perfectly showing it perfectly here, but the bond with the greatest convexity is actually bond 3 because it has the most curvature here. So given changes in the yield to maturity, and it's not perfectly symmetrical because I wanted to go through for a 10% range in the change of the yield to maturity, but you can't go lower than -4% here because then you would have some negative yields to maturity and it messes everything up in the calculation. So I went from -4% to +6%, but even if we cut it off at +4% here, you can see that unless the interest rates go up considerably, your best bet between bonds 2 and 3 would likely be bond 3 because it has more curvature there. There's a greater payoff if the yields to maturity go down, and the additional loss for an increase in yield to maturity is slightly more than bond 2, but not as much as if the rates decrease. So again, just to kind of sum everything up here, bond 1, our blue line here, has the lowest duration, and you can see in our graph that it has the lowest interest rate risk, the lowest change in the value of the bond given a change in the yield to maturity. The bond with the greatest convexity is bond 3. It has the most curvature. And again, comparing 2 to 3, you probably, at least in my opinion, would probably be a little bit better off with bond 3 than with bond 2, assuming that you don't have predictions about the future interest rates. So that's it for this video. It's a lot of information. Please let me know if you have any questions.